So our main focus today is to focus on chapter 10. And in chapter 10, we focus on confidence intervals and hypothesis testing for means. The simplest situation is when you are doing confidence intervals and hypothesis testing for one mean. We've already done that. In chapter 10, it's about comparing means. Chapter 10, the main topic is comparing means. Though there is an important subtopic to help you understand how to compare means, in that it's helpful to also understand how to compare variances. But let's first focus on the means. So you've got two populations, population 1 and population 2. And remember, most people, when they think of the word population, they're imagining people or companies or, baseball players or something like that. And they're trying to study something about that population. But for us, populations really represent a more abstract idea. They're really representing distributions, random variables, you might say, that we're trying to study. We're trying to estimate parameters for those variables like means and variances, that kind of thing. And we've got two samples, two random samples, sample 1 from population 1 and sample 2 from population 2. Random samples. In the abstract, that means we've got, in each case, a certain number of random variables from the same distribution as the population. They don't take on necessarily the same observed values, right? But they have the same distribution. They have the same, for continuous random variables, PDFs, for example, and they would have the same means and that kind of thing. They don't necessarily have the same sample size. N1 and N2 could be different. But we also need one more assumption. We assume that these two samples are gathered independently of each other. In practice, that means you got some mechanism that is choosing the samples in both cases, that, like random number generation is not, the choice of one person or random variable from this population is not affecting the choice there. Independence in the abstract is related to joint densities, as we talked about in chapter 5, but we don't have to worry about the technicalities there. It's the usual song and dance. We want to do two main things. We want to, first of all, do confidence intervals. Secondly, hypothesis testing. And as usual, the hypothesis testing is harder than confidence intervals. Let's talk about the confidence interval first. First, we do a confidence interval to estimate what would it make sense to estimate when we're comparing means. What would it make sense to do here? What are we trying to estimate? Mu1 is a mean for this one, mu2 is a mean for that one. What have we done with proportions? Yeah, estimate the difference. We're trying to estimate mu1 minus mu2 because that would be one number that tells us a relationship between mu1 and mu2. If this number is positive, then mu1 is bigger than mu2. If it's negative, then mu1 is less than mu2. If it equals 0, then mu1 equals mu2. Now, again, in reality, it's kind of a dirty little secret. In all likelihood, mu1 is not equal to mu2. But if your confidence interval contains both positive and negative numbers, and meaning it contains 0, then you don't have much evidence that they're different. And if your null hypothesis is that they're equal, which is the usual case, then you would not reject it because you give the null hypothesis the benefit of the doubt. Right? These same themes come across in new situations. You got your point estimate. X1 bar minus X2 bar is a logical point estimate, or estimator, I should say, in the abstract. Right? Estimator, or estimator for short, is an abstract idea. It's a statistic that we hope is unbiased in estimating the population parameter. This is a number. That difference right there is some fixed but unknown number. This is a statistic. It's a random variable in the abstract. It's got a distribution. In the continuous case, it's a continuous density. What's its mean? Let's do a little side calculation. What's the expected value of x1 bar minus x2 bar? You would hope it's mu1 minus mu2. Is that the case? Yeah. Because you can do this. We can say it's the expected value of x1 bar minus the expected value of x2 bar. Why can we do that? It's a one-word answer. Starts with an L. Linear. I say linearity. Linearity of the expected value operator. Like a derivative. A derivative of difference is the difference of the derivatives. Here, the expected value of a difference of two random variables is the difference of the expected values. Actually, linearity of an expected value operator is not as easy to prove as it is for derivatives. We actually just accepted it. We didn't really prove it. It's harder to prove than you might think. But it's natural. It seems logical. X1 bar is an unbiased estimator for mu1, so this equals mu1. X2 bar is an unbiased estimator for mu2, so this is minus mu2, and we're done. It's a two-step proof. X1 bar minus X2 bar is an unbiased estimator for mu1 minus mu2. So that's your point estimator, and when we observe a value, we would call it a point estimate. Plus or minus a margin of error, I could call it capital E. I guess I will at first. And what is capital E? It's always takes the form of, so far at least, some special number, a Z value or a T value, you could call it a critical value, times some sort of standard deviation. That's what we've seen so far. Why do I say some sort of standard deviation? I'll get back to that. Since we're dealing with means here, and since the population variances are going to be unknown, we're going to use T. We're after a 100 times 1 minus alpha % confidence interval, as usual, where, for example, 95% confidence alpha would be 0.05. So this would be T sub alpha over 2. What is the standard deviation that we multiply by? Well, it depends on different assumptions that you make that may or may not be so valid. In general, the best thing to use here is the square root of S1 squared over N1 plus S2 squared over N2, where S1 squared is the variance for population 1, sample variance, S's, not sigmas. S2 squared is the sample variance for sample 2 from population 2. N1 and N2 are the two different sample sizes. However, this is not always the formula that's used. Sometimes instead, we do it kind of like we did with proportions. We did the pooled proportion in chapter 9. Sometimes we pool variances. But how do you know when to pool the variances or not? I'll come back to that. For the moment, I'll say, or maybe we pool or pool the variances. What was a pooled proportion? Essentially, you're taking your two samples and merging them into one to get a new proportion that you would hope is a better estimator for the true population proportion. Similar kind of idea here, not the exact same kind of formula though. Or maybe we pool the variance, ... We'll come back to that. Gives us a different formula if we do. Another question, though, is what degree is a t here? So there must be a degrees of freedom. df equals question mark, question mark, question mark. What is it? Is it n1 minus 1? N2 minus 1? Something else? The answer is it depends. And it's a very, very wishy-washy depends, because it also depends, well, not only on the assumptions you make, but your philosophy of confidence intervals and hypothesis testing. It's affected by your philosophy. What am I talking about? Whether you are conservative or not. And I don't mean conservative politically or not. You could be liberal politically and still be conservative statistically. Okay. Talk more about this in a little bit. What about hypothesis testing? Hypothesis testing. Just like with proportions, when we're comparing means, the null hypothesis most typically is that they're equal. Mu1 equals mu2. One more time for emphasis. I should never, ever, 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 ever see X bars there. I saw it from a few people in the last exam. No, never, ever, ever. Okay, don't ever put X bars in your hypotheses. It's always population parameters. If you're talking about means, it's always mu's. What's the alternative hypothesis? Well, it could be right-tailed, left-tailed, or two-tailed. Sometimes Dr. Wetzel would write that like this. It could be one of these three, right-tailed, left-tailed, or two-tailed. I'm writing all three of these, but again, in any one problem, it would be just one of them. One point of philosophy here that I haven't mentioned is that some people always do two-tailed tests. Even when they have a theory, maybe that mu1 is bigger than mu2. Why? Why would they do a two-tailed test if they think mu1 is bigger than mu2? Because they're conservative, statistically speaking. Why? Or what does that mean? It means they're trying to make it harder for themselves to reject the null. They're trying to make it harder to make a type 1 error, because when you do a two-tailed test, you double the one-tailed p-value. And your p-value is bigger. Makes it harder to reject the null, makes it harder to make a type 1 error. That's one way to play it conservative, statistically speaking. With confidence intervals, playing it conservative is using a lower degrees of freedom than maybe you need to make your t bigger than maybe is necessary, to make your margin of error maybe bigger than is necessary, to give you a bit more cushion in your confidence interval than might be strictly necessary based on your level of confidence that you're after. That's what I'm talking about. I'm going to say playing it conservative with statistics. I guess we need a t-statistic. T is our test statistic. There we use the sample means, x1 bar and x2 bar. x1 bar minus x2 bar would be your point estimator. Minus the null value is what we typically do, right? When you're standardizing here. Take your x bar or your p hat, subtract the null value and divide by some sort of standard deviation, really more of an approximation to a standard deviation. But what's the null value here? Is it mu1? Is it mu2? No, it's 0. If we're testing mu1 equaling mu2, that's equivalent to mu1 minus mu2 is 0. we'd be subtracting 0 here, which you don't have to write because when you subtract 0, it doesn't affect anything. I mean, I could write it for emphasis. Actually, the book gives you a more general formula here. They give you what they call the pooled t-statistic that looks like this, and there's a typo. Typo. That 0 should not be where it is right there. It should be the subscript of mu1 minus mu2. They're using a capital T here. I should have used a capital T as well. Let me use a capital T. Because it is a random variable. When you compute it, you could call it a little t. What goes down here? In general, it's the same thing as you see up here. S1 squared over N1 plus S2 squared over N2, but the same comment applies. Or maybe we pool the variance. And like once again, we can ask what's the degrees of freedom? DF equals question mark, question mark, question mark. There's 3 different answers for what DF could be. 3 different answers based on literature I've seen. 2 of which are in a book, and the 3rd one of which is not. Though to tell you the truth, I'm conservative statistically, so I like the one that's not in the book. It's also the easiest one to use. The conservative approach to the DF in both of these cases is to take the smaller of N1 minus 1 and N2 minus 1. That's not in our textbook. Our textbook doesn't advocate for that. But I have seen it in another textbook, a couple other textbooks actually, as sort of just a simple thing to do that does play conservative, that tends to give you a smaller DF than the other methods do. And if it's a smaller degrees of freedom, that's going to make this critical value bigger because the t distribution will have a bigger standard deviation when the DF is smaller. It's when the degrees of freedom goes to infinity that the t distribution looks more and more like a normal distribution, standard normal. So it tends to make this bigger, giving you a bigger margin of error. And with this hypothesis testing, it gives you, with a smaller DF is going to give you a bigger p-value, making it harder to reject the null. So that's playing it conservative. But again, this is not in our book. I guess since it's not in our book, you're not going to use this on homework or the exams, but I just wanted to let you know about it. I have seen it in other books. 2 other approaches that are in our book. When we do pooling, when we use a pooled variance approach, DF turns out to be N1 plus N2 minus 2. Weird. Although when you think about it, that's nothing other than N1 minus 1 plus N2 minus 1. It's like you add the degrees of freedom for the 2 separate random variables. That's when you pool the variances. But you have to have justification for pooling the variances, which is the other topic for today. When you do not pool the variances, unpooled variances, so I should use plural there. DF is, well, a nasty formula. Very, very nasty formula. In fact, I've only tried this formula a couple times by hand in my life. Smith-Satterthwaite degrees of freedom. Yeah. I'm not even going to write it down. It's on page 348. It's a fraction within fractions here. A bunch of fractions within fractions. One big overall fraction, this thing on top divided by this thing on the bottom. This thing on top's got fractions in it as well. S1 squared over N1 plus S2 squared over N2, all quantity squared. This one's got fractions within fractions itself. Two individual fractions here, that's squared over that, plus that squared over that. Like I said, I've only used this by hand a couple times in my life. Calculator help. I've never done it without calculator help. And those couple times that I've tried it by hand, I think both times I've made mistakes. And it also doesn't give you a whole number, typically. It gives you a decimal. 12.74 degrees of freedom or something. What do you do when it's a decimal? Well, if you're using technology, you don't really care if it's a decimal. If you're using a table, like a t-table, you'd want to round down. Like if you got 12.74, you want to round it down to 12 instead of up to 13, because rounding down plays it conservative. And that's a good idea. Again, whether you're liberal politically or not, it's a good idea, I think, to be conservative statistically. Lowering the degrees of freedom plays it conservative. Again, it makes the critical values bigger, giving you bigger margins of error, and it gives you bigger p-values, making it harder to reject null. But usually, I just avoid using this formula at all, and I just use technology. Let's use some technology right now. So one way we're going to use technology today is with a spreadsheet. Reminding you of how to do simulation in a spreadsheet for one thing. Let's say we're comparing two means, and maybe these means represent two different sections of a calculus class. Maybe it's at a really large university and these sections have thousands of students in them. But you're taking small random samples of a certain size and computing their mean scores on the final exam out of 100. So this is the section 1. And this is section 2. The sample sizes do not have to be the same. That's part of the point here, is the sample sizes do not have to be the same, though they often are. People often use the same sample size, but you don't have to. I, for purposes of illustration, will use two different sample sizes. Let's say section 1. Okay, let's pretend that, you know, as would be realistic, that in reality, the means of these two sections and their variances are slightly different at least. So we could use norm inv along with rand to simulate sampling from a normal distribution. We did this before. And it's a final exam. Maybe the mean for section 1 is 80 and standard deviation is 10. Of course, it'll update these scores all the time. I'll do my copy and paste special over here so I can freeze the scores. So section 1, the true mean is 80 and the true standard deviation is 10. Let's do a random sample of size 5. So N1 is 5. Copy and paste special to paste the values there so they don't get updated anymore. Of course, those got updated. And let's also decrease the decimal places here. Well, let's just go ahead to the nearest whole number. But section 2, let's assume the true mean is different. Instead of 80, it's something else, 82. And the true standard deviation is different. Instead of 10, it's maybe 9. Forgot my rand. Rand, remember, gives you a random decimal between 0 and 1. when I plug such a random decimal into norm in, pretend rand is 0.7 or something. Norm in that case, is effectively giving the 70th percentile. Now, this number 59 is a very small number compared to the mean of 82 here. The value of the rand must be very close to 0 with this particular one. Though when I enter it, it changes it anyway. Let's do a different sample size, say size 7 for section 2. Copy and paste it over. Paste special. Values only. And decrease the decimal. Okay, 2 different samples of test scores from these 2 different sections. Going to focus on these numbers now. What am I wondering? I'm wondering, are mu1 and mu2 the same? Now, of course, with the simulation, the way I did it, they're different. One is 80, one's 82, as would be typical in real life. But that's not the issue. The issue is if I give the assumption that mu1 equals mu2 the benefit of the doubt, do I have statistically significant evidence that they're different? That's the issue. Right? That's always the issue. I'll put these numbers in my calculator too. And we'll compare what the technology gives us. You can do it in your calculator if you like. Stat mode, edit. So list one, 78, 82, 74, 74, 91. List 2 is 83, 79, 86, 62, 71, 72, 89. Again, mu1 in reality is 80, mu2 is 82. Does that mean x1 bar is going to be less than x2 bar? Not necessarily. What are we trying to do? We're trying to compute a confidence interval to estimate mu1 minus mu2. And we're trying to do a hypothesis test on whether mu1 is equal to mu2. And since I don't know, you might say you're not likely to have a theory about whether section 1 is better than section 2 or vice versa. You could do a two-tailed test, or maybe that's your philosophy to always do two-tailed tests. So let's try it with the calculator first. Stat mode, tests. We can do hypothesis tests. We can also do intervals. We're after a t-interval, a 2-sample t-interval is what we want. That's a 2-sample t-interval to estimate mu1 minus mu2. Again, mu1 is 80, mu2 is 82. In reality, mu1 minus mu2 is -2. Will this interval be close to -2? It's hard to say. These sample sizes are small. So it's very likely that it may not be centered very close to -2. Could even be centered on a positive number. 2-sample t-interval. We've got data, not stats. List 1 and list 2. Leave the frequencies at 1. C level, that's the confidence level. Pooled, yes or no? Well, how do you know whether to pool the variances or not? You pool the variances if there's not evidence. Well, if you think they're likely to be close to equal and there's not evidence that they definitely differ. Is that the best way to say that? You pool the pot of the sample variances, S1 squared and S2 squared, if you suspect the population variances are equal, or at least really close to being equal. And after doing a statistical test that I'm going to describe shortly, you don't have evidence that they differ. Let's just see what happens to the answer, whether I pool or not. So if I pool yes, keep that as yes. I'm about to calculate a confidence interval. It will also show the degrees of freedom. What degrees of freedom will it show? It should show, the calculator is doing it according to the book, it should show this degrees of freedom, n1 plus n2 minus 2. 5 plus 7 minus 2 is 10. Yep, 10 degrees of freedom. There's the interval. It's centered on it's centered, and it should be the same answer you get if you type the numbers in like me. It's centered on a positive value. X1 bar is bigger than X2 bar, even though mu1 was less than mu2. That can happen with random sampling. Now, if the sample sizes were much larger, it would be unlikely to happen. But there's your confidence interval. You can write that down if you want, based on pooling with 10 degrees of freedom. X1 bar is 79.8, X2 bar is 77.43. S1, the sample standard deviation for sample 1 is about 7.1. Corresponding S1 squared variance would be that number squared, around 50. S2, sample standard deviation for sample 2 is about 9.6. The variance would be what you get when you square that, somewhere in the 90s. SXP, or just SP for short, that's the pooled variance. You can obtain the pool, well, that's the pooled standard deviation, excuse me, square root of the pooled variance. You can obtain the pooled variance from the individual variances in a way I haven't shown you yet. N1 is 5, N2 is 7. Okay, yeah, all those numbers are in their degrees of freedom. Is 5 plus 7 minus 2. All right, what if we do the same thing? So this answer was negative 8.9 to 13.7 approximately for this example. Pooled. Approximately negative, okay, I'll write more decimal places. 8.931 to 13.674. And for reference sake, X1 bar minus X2 bar is 79.8 minus 77.429 approximately. What, 2.371? This is the 13 here. That's the center of this interval. What's the margin of error? You can figure out the margin of error by doing the right endpoint 13.674 minus the estimator value 2.371. Looks like the margin of error, the observed margin of error, is about 11.3. Yes, this contains both negative and positive numbers. It contains 0. We don't have much evidence that mu1 and mu2 differ. We don't really have any evidence that they differ. What if we did not pool? Unpooled. It's the same point estimate, but we get a different margin of error. Go back to the stat menu. Go to tests. To sample t interval. Go to no instead of yes. What's the calculator going to do? It's not going to do the conservative approach. It's going to do the Smith-Satterthwaite, I think. I've never checked it. I suppose I should. And what will Smith-Satterthwaite produce for the degrees of freedom? It's hard to say ahead of time. So it's not pooled. Calculate. Is producing 9.95 degrees of freedom, not a whole number. It's producing this interval. It's a little bit bigger. Is that because the degrees of freedom went from 10 to 9.95? It's not the whole reason. It's also that the formula is a little different for, well, this quantity ends up being different. When you pool, you replace both S1 squared and S2 squared by the pooled variance. And the formula simplifies. When you use SP squared, the pooled variance, this becomes, you replace both of those with the pooled variance, and then you can pull it out and take its square root. And you get the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. Kind of similar to what happens with pooling proportions. And that's what you get there. And it's also what you get down here. I took the variance out of the square root as a standard deviation. This pooled variance replaces both of these things. It can be factored out, take the square root to get rid of the square. So this thing changes a little bit too. But what is the pooled variance? I still haven't written down the unpooled answer here. The pooled variance is a weighted average of the individual variances, but it's a weird weighted average. It's n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared over the sum of those two, n1 plus n2 minus 2. That's how it's computed. If n1 equals n2, if the sample sizes are the same, it gives you the average of s1 squared and s2 squared. But in general, n1 and n2 are not equal. Anyway, coming back to the unpooled, what was the answer? It was a little bit bigger interval, 8.351 to 13.094. Excuse me, a little smaller interval. Yeah, generally speaking, when you lower the degrees of freedom, it actually gives you a bigger interval. But because we're not pooling here, it changes this enough that we actually get a smaller interval. This difference is still the same, but now the margin of error is a bit smaller. 13.094 minus 2.371. Our margin of error is under 11 this time. What about hypothesis testing? So in both cases, the final conclusion is the same. We've got both negative and positive numbers in the interval. We don't have much evidence that mu1 and mu2 are different. What about hypothesis testing? Again, there's the t-statistic you use. In the case where you pool the variances, you replace both of those with the pooled variance, which means that thing goes in the bottom of the fraction. These formulas are all in the book. Instead of this thing. Which does mean you get a different t-statistic. You also get a different p-value. Let's see what happens. Go back to stat. Go to tests, but now we're not doing an interval. Instead, we're doing a two-sample t-test. It's assumed to compare means there. Again, we have data, list 1, list 2, keep their frequencies at 1. Let's do a two-tailed test. Again, we have the option of pooling or not. We'll do it in the same order as before. If yes, we pool. Let's go ahead and draw the area that we calculate as well, just for the sake of doing it. It will be a t-distribution that we're looking at. And it's a very big area. P-value is very large, 0.65. The observed value of the t-statistics, 0.4675. You'd want to report that. So we're testing the null that they're equal versus the two-sided alternative. mu1 is not equal to mu2. If we pool the t-statistic, the observed value is 0.4675, not very extreme, right? Not far from zero. What's far from zero? Well, certainly if you get like 3 or more, or -3 or less, that is what we tend to think of as being far from zero. Not very extreme. The p-value is not going to be very small. It's going to be relatively large. You can see it here. The p is approximately 0.65. Definitely do not reject the null. We don't have strong evidence against it. It's not showing the degrees of freedom here. If we had done the test without graphing it, would we see the degrees of freedom? Just calculate. Yeah, degrees of freedom is 10. That's 5 plus 7 minus 2. Same x1 bar, x2 bar as before. Same standard deviations and pooled standard deviation as before. You could write these numbers down if they're requested. And it would be good for you to not just use your technology in this way. It would be good for you to check the formulas too. Maybe you should default to that and then just check that the technology gives it the same answer. Do not reject the null. If it's unpooled, two sample t-test, go down to no. I'll just have it calculate. That's where we get the 9.95 degrees of freedom. Very close to 10. Are they always close? Does Smith-Satterthwaite always give you something close to n1 plus n2 minus 2? No, they're not always super close. Okay, so realize that. Don't be surprised if they're relatively far away from each other. The p-value, the t-statistic in this case it is a bit different. Oh, where'd it go? Sorry. The observed value of the t-statistic is a bit different, 0.493. Why? Because when we pool, we use this formula, except this thing is in place of that. When we don't pool, it is, like you see it there. It's not surprising then that you get something different, slightly different. P-value is approximately 0.63. Slightly smaller, but still pretty big. Do not reject the null. What does the conservative approach give you? What if we use degrees of freedom equals n1, the smaller of n1 minus 1 and n2 minus 1? What were n1 and n2? n1 was 5, n2 was 7. The conservative df would be the smaller of 5 minus 1 and 7 minus 1 would be 4. If we did the same test with that approach, the t-statistic would still be the same, because I would still use this formula for the t-statistic. But the p-value would be different. I'd have to go to my distribution menu and go to inv t to figure out the p-value. No, not inv t, but tcdf, excuse me. tcdf, what's the area to the left of 0.493 when there's 4 degrees of freedom? It's going to be bigger than 0.5. Let's guess what to expect here. I say when you use the conservative approach, you get a bigger p-value. So I'm expecting something bigger than 0.3 when we use this approach. Meaning the area to the left of 0.493 should be smaller than 1 minus 0.63. 1 minus 0.63 is 0.37. You should get something smaller than 0.37 here. Wait a minute. Oh, I'm forgetting about the fact that this is a two-tailed test. Sorry. What do we get? We get something bigger. Okay. What this is showing is that for 4 degrees of freedom, for T4 distribution, the area to the left of 0.493 is 0.676, meaning the area to the right of that is 1 minus 0.676, is 0.324. But for the p-value for a two-tailed test, you got to double that area. So the p-value is 0.648. Yes, a little bit bigger than that. Not bigger than that, but bigger than that. Just slightly, but if the p-value were close to 5%, it could make a difference if you were using alpha equals 5%. You are making it harder to reject the null. Paying attention okay? Stats is definitely more exciting when you're doing it on your own, like in real life. Oh, maybe my boss will give me a bonus if I do well on the stats project that they've given me. You know, that's when it's more exciting. Or when you deal, even if you're not going to get a bonus for doing it, just the fact that you're doing it on your own in the real world. Well, that's exciting. It's maybe a little scary. Have some coworkers that you work on it with again. Can the spreadsheet confirm these answers? It's good to know whether it can or not. Let's just compute the means and variances first and confirm the answers we got for those in the calculator. So equals average to compute a mean. I think I can go on to D8, even though there's no numbers in D7 and D8. Fine. Yeah. Oh, wait a minute. Why did we get 80 there? Is it rounding? Okay, it's rounding, I guess. So it's 79.8. That's what I was on the calculator. Did I type something wrong? The mean is coming out different. So, okay, no, I got 79.8 before. Okay. All right. I'm confused. Why are we getting not 79.8 here?
I don't know if section 1 rounded the right way. I thought I saw some that under.
Oh, it's okay. It's using the full decimal places instead of the rounded numbers. That's why. Okay, maybe I should retype these over here. On my calculator, I was using the fully rounded numbers, but the spreadsheet is keeping more accuracy internally. There we go, 79.8. And 77.429. What are the standard deviations? What's S1? Equals FTDEV. .08. Is that what we got in the calculator? Let's double check that. We could do either the t-test or the interval. Let's look at the t-test here. .085. Yep, 7.085. You got to square those if you want to see what the variances are. And then we could also see what the pooled variance is. N1 minus 1, 4 times S1 squared, plus N2 minus 1, 6 times S2 squared, all over N1 plus N2 minus 2, 10. 5 plus 7 minus 2. Pooled variance 75.05. Pooled standard deviation then would be the square root of that. .663. Oh, we didn't pool here. Go back and pool. 8.663. Yep, there we go. So we're confirming those numbers. What about the test? What could we do here? We could do perhaps equals t-test. Range 1, range 2, tails and type. What's this going to do? This hypothesis test to compare the two means, a t-test. It seems to be assuming we've got two different samples from two different populations. How many tails is two-tailed? What does type mean? I think the type is referring to whether we pool or not. Maybe 0 don't pool and 1 do pool. Maybe. I'm guessing. Can probably look it up. Not available. Oh, it doesn't like the fact that I'm using different sample sizes. Oh, you're kidding. Array arguments to t-test are different size. That's not so nice. So it seems like the spreadsheet can only do this when the sample sizes are the same, which is not so much fun. It's more fun when they're different, right? We could try to calculate the observed value of the test statistic. In the case of pooling, it would be, watch what I type here, x1 bar minus x2 bar minus 0 divided by the pooled standard deviation times the square root of 1 over n1, which is 1/5, plus 1 over n2, which is 1/7. 0.467, is that what we got before when we pooled? For the t-statistic? Yep, 0.467. And for the p-value for that, equals t-test is supposed to return a p-value. But it didn't like the fact that my sample sizes were different. But I could do equals t-dist here with this number. I'm pooling, so I use 10 degrees of freedom. It's two-tailed, 0.65. Yeah, matching that. If I made them the same sample size, does t-test work? It should, I hope. Let's just make these the same sample size. Let's make this, to add some more data here, 80 and 83. Let's see if equals t-test does it if they're the same sample size. Two-tailed, 1 for pooling. Okay, that's supposed to be a p-value. It's a little smaller. This mean got a bit bigger. That's why it ended up being a little smaller. Okay. So I'm showing you how to use these formulas or to do this kind of stuff with technology, calculator and spreadsheet today. But you should make sure on the homework that you practice with these formulas too. This one with the confidence interval, substitute that when you pool. This one with the hypothesis testing, substitute this for that when you pool. When you pool, use this degrees of freedom. When you unpool, use Smith-Satterthwaite or technology. DF equals technology. I'm not going to test you on Smith-Satterthwaite. You won't have to use it on the test. Though maybe you have to use technology. There's one more thing to do today. How do you know when you can pool or not? Pool variances or not? Again, people tend to pool when they think the variances are equal or at least close. And they haven't done tests to see whether there's statistically significant evidence that they differ. Then they go ahead and pool. It's just simpler, you might say. At least it was before calculators and spreadsheets came along. Now we might as well just use the technology. But in general, we do want to be able to do a test about whether the population variances are equal or not. And if we reject the null hypothesis in this context, the advice is don't pool. So maybe people pool anyway. Yeah, you know, people misuse statistics. They might end up pooling anyway. You should be aware of that. But again, you give the null hypothesis the benefit of the doubt. This is the test we want to close class with today. But this begs a question. What's the test at? It's called an F statistic. F statistic. We have never used the F statistic before. That's okay. Before chapter 8, we never used the t-statistic before. It's a new statistic. What does it equal? It equals the ratio of the sample variances. This is an F stat. With certain degrees of freedom. And it's not 1 degree of freedom, one formula for a degree of freedom. It's 2 different formulas for 2 different degrees of freedoms. N1 minus 1 and N2 minus 2 minus 1 degrees of freedom. And you don't add those things. We're not using one number representing 1 degrees of freedom. We're using 2 numbers representing 2 degrees of freedom, 2 separate things, one of which is for the numerator and one of which is for the denominator. This F statistic is meant to compare the variances. Wait a minute, doesn't that mean we should use a difference? I mean, we've done that before, P1 hat minus P2 hat, and X1 bar minus X2 bar, to compare means and proportions. Well, you could try using a difference, S1 squared minus S2 squared. However, it's better to use a ratio, a quotient here, because it's just simpler. It's a simpler distribution to work with. You're going to have strong evidence against the null hypothesis if this ratio is much bigger than 1 or much smaller than 1. Now, what does that mean? What's much bigger than one and what's much smaller than one? That depends on the degrees of freedom. But, if this were 3 or larger, that's pretty far from one, above one. If it were 0.3 or smaller, that would be pretty far from one, below one. When this ratio is close to one, then we don't have much evidence that these things differ. You do try to set this test up in such a way that after you've gathered the data, S1 squared is bigger than S2 squared. You try to set things up that way, so you can focus on values of this that are bigger than one. Does that happen with our example here? I don't know. Looks like, yeah, S1 squared is less than S2 squared. So with this example, we want to switch around the roles of which one's S1 squared and which one's S2 squared. The observed value of our F statistic for this example, put the bigger number on the top, is the way you want to do it. So in reality, if I'm thinking of sample 1 as being the G column for section 1 and sample 2 as being the H column for section 2, instead of doing S1 squared over S2 squared here, I really did S2 squared over S1 squared. Put the bigger one on top. Yeah, 1.825. There's our observed value of the F statistic. What do you do with it? Same thing you do with Z and T. Use it to find the p-value. The one-tailed p-value, so we got 1.825 here. Our observed value of the F statistic based on 4 and 6 degrees of freedom. $91.619 divided by 50.2. That's approximately what we get, 1.825. What does the F distribution look like? It looks like this typically. It's not symmetric. It's not a normal curve or a t-distribution. The right-tailed p-value would be the area under this curve to the right of 1.825. That's the right-tailed p-value. What does it equal? Use technology or a table. On a calculator, you want to use your distribution menu. FCDF. This will compute the area to the left of 1.825. Numerator degrees of freedom is the 4. Denominator degrees of freedom is the 6. There's a degrees of freedom that's associated with the numerator and one with the denominator, n1 minus 1 and n2 minus 1, where again, the convention is to put the bigger one on the top as far as the variance itself goes, not the degrees of freedom necessarily being bigger. Oh, you know what that means though? Actually, it means we need to switch those around, doesn't it? 6 and 4. And I should switch these around, 6 and 4. Because for this example, it was really the second sample size that had the bigger variance. The second sample having the bigger variance. You might wonder whether it makes a difference or not. .708. Double it to get the two-tailed p-value. That's going to be bigger than 1. P-values are probabilities. Probabilities can't be bigger than 1. Okay, so doubling this number doesn't really give you, in a sense, oh, wait, oh, sorry. Got to do 1 minus that. Okay, that makes more sense. 0.292. But it is still true that doubling this You might say it doesn't technically give you a rigorously defined two-tailed p-value because this distribution is not symmetric. But people double it anyway. And that's what the book says to do. Two-tailed p-value is, let's just go ahead and hedge our bets by writing approximately. Approximately 2 times 0.292, 0.584. Not very small. Don't reject the null. So we're happy. We're not rejecting the null. We get to pool when we compare the means, which makes us happy, especially before technology. Could I compute this p-value with the table? Yeah, there is an F table in the book. It's not a very pleasant table. It's over many pages. Starts on page 704. F distribution. And goes over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I lose count? 11 pages? Yikes. How do you use it? The gamma 1 is the degrees of freedom for the numerator. The gamma 2 is the degrees of freedom for the denominator. The first half of these correspond to CDF values that are 0.9. The second half of the table corresponds to the CDF values that are 0.95. Okay, our numerator had 6 degrees of freedom and our denominator had 4 degrees of freedom. 6 for the critical value is 4.01. That's the number on the horizontal axis where the area to the left is 0.9. Our F statistic was smaller than that. So the area to the left of our F statistic was less than 0.9. Yeah, it was 0.708 or whatever. Meaning the area to the right is bigger than 0.1. It's, in this case, it's 0.584 or 0.292 for the one-tailed. I went kind of fast for such a confusing table, but we're out of time. Rely on your technology for that part. Try using the table, try understanding the table. I did give you the basic idea. It just, I know, went by in like 1 minute, and that's not really enough time to fully understand it. All right, have a good day.